Welcome back to AI.Code.Cast. Today, we're going to be diving into a classic coding problem that's deceptively simple, on the surface, but it reveals some really fascinating algorithmic insights when you dig deeper. We're going to be building a basic calculator.
It's funny how something we humans do almost effortlessly, like crunching numbers, can be surprisingly complex to teach a computer.
Absolutely, and that's what makes this deep dive so interesting. We're not just slapping together a user interface. We're going deep into the logic of how to make a computer understand and execute mathematical expressions correctly. Think addition, subtraction, and of course those ever-tricky parentheses. We're talking about building the brain of a calculator, not just its looks.
And the real challenge here is to do it without relying on any built-in shortcuts or evaluation functions. No cheating. We're building the logic from the ground up, step by step, just like you would if you were teaching a beginner the order of operations for the very first time.
Exactly. So let's say our calculator needs to handle an expression like 1 plus 4 plus 5 plus 2 plus 6 plus 8. It looks intimidating, but really it's just a combination of basic operations. Where do you even begin to tackle this kind of problem?
Well, the most intuitive approach, I think, might be to just go from left to right, evaluating the expression as you encounter each number and operator. It seems simple enough, right? But that's where the pitfalls begin.
Okay, I'm sensing a but coming. What makes this seemingly straightforward left-to-right approach problematic?
It all boils down to something called operator precedence, the rules that govern which operations should be performed first in a mathematical expression. And in the world of math, parentheses are king. They essentially shout, do me first. And then there's subtraction, which, unlike addition, isn't associative.
Hold on, associative. You might need to break that down a bit for our listeners who aren't, math whizzies.
Sure, associative means you can group operations in different ways without changing the result. Addition is associative. A plus B plus C is the same as A plus B plus C. But subtraction is not. ABC is not the same as ABC. So if you simply go left to right, ignoring the parenthesis and the non-associative nature of subtraction, you'll end up with a very wrong answer.
Ah, I see. So our simple left-to-right strategy falls apart pretty quickly when parentheses enter the picture. It seems like we need a more sophisticated way to teach our computer to respect the order of operations. Any ideas on how to approach this?
There are a few clever ways to tackle this challenge, but one of the most elegant and widely used approaches involves a data structure called a stack. Think of a stack like a pile of plates. You can only add a plate to the top, and you can only remove a plate from the top. This last-in, first-out structure turns out to be incredibly useful for managing the order of operations in mathematical expressions.
Okay, I'm starting to see how a stack might be helpful here, but I'm still a little fuzzy on the specifics. Could you elaborate on how we actually use a stack to evaluate our calculator expression?
Absolutely. Let's stick with our example. 1 plus 4 plus 5 plus 2, 3 plus 6 plus 8. We can use a stack to store numbers and operators as we encounter them, making sure they're processed in the correct order.
So we're essentially using the stack to temporarily hold pieces of the expression until we're ready to deal with them.
Precisely. Imagine you're reading the expression from left to right. When you hit a number, you push it onto the stack. When you hit an operator, you consider what's already on the stack, making sure you're following the order of operations.
Okay, so far so good. But the part that's really tripping me up is the parentheses. How does the stack help us handle those nested expressions?
That's where the stack's last-in, first-out nature really shines. When you encounter an opening parenthesis, you essentially push the current state of your calculation onto the stack. Think of it like creating a save point in a video game.
So we're pausing the main calculation to dive into the nested expression within the parentheses.
Exactly. You can then start fresh with a new total and continue evaluating the expression inside the parentheses. When you hit a closing parenthesis, it's like hitting load game. You pop the save state off the stack, bringing you back to where you left off before entering the parenthesis, and continue with the main calculation.
Ah, that makes so much sense. The stack acts like a memory for our calculator, allowing it to keep track of where it was before diving into those nested expressions.
You got it. It's a beautifully elegant way to manage the complexity of nested expressions without getting lost in a sea of numbers and operators. Welcome back to AI.Code.Cast. Now that you have a good grasp of how stacks can be used to solve the calculator problem, let's look a little closer at some specifics of how this might work in practice.
When you first mentioned stacks, I'll admit my brain went straight to a stack of pancakes. It took me a second to wrap my head around how that breakfast staple could help us solve this coding problem.
Well, Sometimes the most complex concepts can be explained with the simplest analogies. But you're right. Let's get into the nitty-gritty of how we actually implement this stack-based evaluation. Remember our example from earlier? 1 plus 4 plus 5 plus 2, 3 plus 6 plus 8.
Yep. It's permanently etched into my memory now. I see parentheses in my sleep.
Well, let's try to make them a little less nightmarish. One key to making this work smoothly is to treat subtraction as adding a negative number. So instead of seeing 5, 3, we'd think of it as 5 plus minute of 3. This simplifies our logic because we can treat both addition and subtraction with the same set of steps.
That's a clever trick. It's like we're streamlining the operations to make things easier for the computer.
Exactly. Now imagine we're going through this expression one character at a time. We'll need a few variables to keep track of everything. One for the current number we're building, one for the current operator, one for the running total, and of course, our trusty stack.
All right, so we've got our variables all set up. What happens next? Do we just start throwing numbers and operators onto the stack willy-nilly?
Not quite. We need a set of rules to guide us. So let's walk through it. First, if the character we encounter is a digit, we append it to our current number. Pretty straightforward, right?
Okay, so if we see 1, then 2, we know we're building the number 12. Got it. What happens when we hit an operator, like plus or minus?
Ah, good question. This is where we need to be mindful of the order of operations. Before we can handle the new operator, we first need to evaluate any pending operations.
Wait, are we talking about looking back at the previous operator?
Exactly. Let's say our current operator is a plus a, and we encounter a fen. We need to perform the addition using the current total, the current number, and that previous plus a operator before we can even think about the new o we just encountered.
Okay, I'm starting to see how the stack comes into play here. We're essentially using it to remember the operations we need to perform in the correct order.
Precisely. Once we've taken care of any pending operations, we update our current operator to the new one and reset our current number. We're essentially clearing the slate for the next part of the expression.
All right, so we're handling digits and operators. But what about those pesky parentheses? That's the part that's been giving me the most trouble.
This is where the true magic of the stack reveals itself. When we encounter an opening parenthesis, we need to create a save point in our calculation, remember?
Ah, right, like hitting the pause button on the main calculation.
Exactly. To do this, we push the current running total and the current operator onto our stack. Then we reset our running total and operator, effectively pretending we're starting a brand new calculation within those parentheses.
So we're kind of treating the expression inside the parentheses as its own separate problem.
You got it. And when we reach a closing parenthesis, that's our cue to unpause the main
I'm
calculation.
guessing this is where we get to pop those saved values off the stack.
You're a natural. We pop the previous total and operator off the stack, bringing us back to where we were before we ventured into that nested expression.
And then we integrate the result we just calculated within the parentheses back into the main calculation.
Exactly. We use that saved operator to determine how to combine the previous total with the result from within the parenthesis, and voila, the nested expression is seamlessly woven back into the main calculation.
I'm amazed by how elegantly the stack handles all this complexity. Like a behind-the-scenes choreographer, making sure every number and operator takes the stage at the right time.
Now let's see if we can translate this elegant dance into some approachable pseudocode.
Now that's what I'm talking about. Let's get practical. Welcome back to AI.Code.Cast. We've been exploring the inner workings of calculators, and we've tackled some tricky concepts like operator precedence, and we even ventured into that mind-bending world of string reversal. But believe it or not, there's another intriguing approach to this problem.
You're referring to the string reversal method, okay?
Exactly. Now, I know this might sound a bit counterintuitive at first, reversing the entire expression before we even start calculating, but trust me, it's a pretty slick technique.
It might seem strange initially, but it actually simplifies the logic quite a bit. Remember how we talked about our brains naturally wanting to solve what's inside parentheses first?
Yeah, it's like we're hardwired to tackle those nested expressions before anything else.
Well, by reversing the string, we're essentially flipping the order of operations, making it easier to process everything step by step using our trusty stack.
Okay, I'm all for making things easier, but how does reversing the string actually achieve that? Can we walk through an example?
Absolutely. Let's bring back our old friend. 1 plus 4 plus 5 plus 2 plus 6 plus 8. If we reverse this, we get 8 plus 6 plus 3, 2 plus 5 plus 4 plus 1. Notice how the parentheses are now in reverse order. That's a key part of this strategy.
Okay, I see the reverse string, but I'm still a bit foggy on how this actually helps us with the calculation.
Let's break it down. Imagine we're processing this reverse string, character by character, just like before. We'll still use a stack, but we'll use it a bit differently this time.
So the stack is still our trusty sidekick, but it's playing a new role in this reversed world.
You got it. Instead of using the stack to store the state of our calculations while we delve into parentheses, we'll use it to hold on to numbers until we're ready to perform an operation.
Okay, that's a twist. So if the first character we encounter is 8, what do we do?
Since it's a number, we simply push it onto the stack. No need to overthink it. Then, if the next character is an 8 plus 8,
We push that onto the stack too.
you're catching on quickly. We're
Yep.
essentially queuing up the operations. Then, if we see a 6,
We'll push that on the stack as well. So now we have 8 plus A and 6 all stacked up. What happens next?
here's where it gets interesting. The next character is a closing parenthesis. In this reversed world, that closing parenthesis actually marks the end of a subexpression, the 6 plus 8 from our original string.
Ah, so the parentheses, now in reverse, are acting like signals to perform the pending operations.
Exactly. When we hit that closing parenthesis, we know it's time to do some math. We pop the 6, then the 8 plus, and finally the 8 off the stack. We perform the addition, 8 plus 6, which gives us 14.
And then we push that result, 14, back onto the stack. So we're essentially replacing the sub-expression with its calculated value.
Precisely. It's like we're simplifying the expression as we go. And we continue this process as we encounter more closing parentheses, each time evaluating the corresponding sub-expression and pushing the result back onto the stack.
It's like those Russian nesting dolls where we keep opening them up, evaluating what's inside, and then replacing them with a single value.
That's a great analogy. And by the time we reach the end of our reverse string, the final result of the entire expression will be sitting there on top of the stack, waiting for us to reveal it.
This string reversal method is pretty mind-bending, but I have to admit, it's kind of brilliant. It seems like both this approach and the stack-based approach without string reversal are quite efficient, right?
They are. In terms of their big O notation, which is a way to describe how the performance of an algorithm scales, both methods have a time complexity of O, where n is the length of the input string. This basically means they both process the expression in a linear fashion, taking a predictable amount of time based on the length of the input.
Okay, so they're both efficient in terms of time. What about space complexity? I mean, couldn't the stack get really large for complex expressions?
That's a valid point. The space complexity of both approaches is also ON in the worst-case scenario. This means that the amount of memory they use is also proportional to the length of the input. However, in practice, the actual memory usage might vary slightly depending on the structure of the expression.
I see. So both approaches are efficient and have similar space requirements. Is there any reason to choose one over the other?
The choice often comes down to personal preference and the specific context of the problem. Some programmers find the string reversal method to be a bit more intuitive as it closely mirrors the way we naturally solve expressions by hand.
I can see that. Reversing the string and then processing it step by step almost feels like we're unwinding the expression, making the order of operations more explicit.
Exactly. On the other hand, the stack-based approach without string reversal can be more memory efficient in some cases, especially for deeply nested expressions.
So it's a trade-off between intuitive simplicity and potential memory savings.
You got it. Ultimately, the best approach depends on the specific requirements of your project and your own coding style.
Well, this has been an incredible deep dive. We explored the inner workings of calculators, tackled those tricky concepts like operator precedence, and even ventured into that mind-bending world of string reversal. Who knew something as seemingly mundane as a calculator could be so fascinating?
It's a great reminder that even the most everyday tools we use rely on these complex and elegant algorithms under the hood. And understanding these algorithms can not only make us better programmers, but it can also deepen our appreciation for the power and beauty of computational thinking.
Well said. Thanks for joining us on AI.Code.Cast. Until next time, keep those algorithms humming.